Now I am going to explain the mechanism of nucleophilic substitution reaction. So mechanism is of two types, and it is SN2 and it is SN1. SN2 it is called as bimolecular nucleophilic substitution reaction. Bimolecular, bi means two. So two molecules they react together, but actually the processes they take place together. So here it is nucleophile. Here it is nucleophile, and this is the halide. This is the haloalkane having halide group. So this is having carbon having delta positive. This will have delta negative charge. So the molecule is polarized. So this is the attacking species. OH is attacking species. So it will attack here on this place from this side. This is very important to note that all the chemical reactions they have their own mechanism and they proceed in a particular manner. So as a result of this attack, here this OH will be attached to this carbon. Here there is the carbon. So this is dotted line indicates the temporary bonds. And this group is called incoming group. This group OH is called as incoming group, and this this is said to be the outgoing group. And this is this in the square bracket it is intermediate compound, or the compound of transition stage. This is neither the reactant nor the product. The incoming group is coming progressively and the bond becomes stronger, and so here this bond is slightly weaker. Similarly, this is going to be slightly more and more weaker with respect to time, and this will become stronger. So as this will become stronger, this will become weaker, and so at last there is the formation of the product. And so see children, the inversion, this is called as inversion of configuration. The structure here, see, this is bone line notation. Here this plane straight line indicates on the axis. This indicates dotted line indicates the away from the observer, and this wedge indicates towards the observer. So as a result of this, the same thing is reversed here, and so this is the product, and this is the halide ion, and so it is having the inversion of configuration. We use inversion means just reverse. We have invert in our homes. What happens when main supply goes away or main supply fails? We are connected with inverters in our homes, and automatically inverter switches it on, and so we are able to get the electricity. But as soon as main supply is on, what happens? Inverter starts charging and it stops. So this is inverter. Similarly, you can compare the umbrella. Where there is very high speed wind, umbrella it gets reversed, inverted. So same is the case. Inversion of configuration is very important point in this mechanism of haloalkanes. Now next point related to it is relative reactivity of different haloalkanes. We have the primary haloalkanes, we have secondary, we have tertiary. Now see, I am drawing here carbon X, H, H, H. This is primary. Now coming to secondary. In case of secondary, here we have X, here we have C, here we have C, here we have H. This is secondary. Now here I am drawing this R, here we have R, here we have R, here. Here we may put here R for any polarity. Now see, you know about the steric hindrance. And so here, these groups, alkyl groups, they are very bulky. And so they have the electron density around themselves. These groups are bulky groups, and so they have steric hindrance. They have effect of steric hindrance, means they create electron density, and so steric hindrance there is repulsion. There is repulsion among themselves, and alkyl groups, they have the tendency, and as a result they are less polar. Similarly, here there are the three bulky groups. In case of tertiary, three groups are present, and so it will be most reactive. So you have to keep in mind that primary haloalkanes are most reactive. Primary haloalkanes are most reactive, followed by secondary, followed by tertiary. Why tertiary are least reactive? Tertiary are least reactive. Least. It is most. Because in case of tertiary, there is the maximum steric hindrance due to three bulky groups. Three groups which are bulky. And as a result, tertiary haloalkanes are least reactive. Now I am going to explain another very important point, and it is unimolecular nucleophilic substitution reaction, and it is called as SN1. So far you have seen the SN2 bimolecular. So in case of bimolecular reactions, the chemical change takes place, the two steps takes place together. But here in this, it takes place in the two different steps. So first step, here there is the tertiary haloalkane, and this takes place in protic solvent like alcohol or dilute acid. So it undergoes, have different mechanisms. There is the formation of carbonium ion or carbocation. So it is lost, and this is the lost halide ion. So this takes place under protic solvent. This you have to keep in mind. Protic solvent means the solvents which provide the proton. So automatically there is the ionization, and there is formation of this is tertiary carbonium ion, and this is reversible. This is reversible and slow. This is reversible and slow. This second step, it is irreversible and it is fast. So here there is the nucleophile. So nucleophile, OH ion again same as it was in case of SN2 mechanism. So again it is same. Polarization is there. This is the carbonium ion, tertiary carbonium ion, tertiary carbocation. So it is able to attack on this in second step, and as a result there is formation of the product. So this is there about the SN2 and SN1 mechanism. In SN1, the two steps are there. This is the tertiary haloalkane, and in protic solvent like alcohol or dilute acid or water, it undergoes self-ionization to form the carbonium ion or carbocation, and this is first step, and it is reversible and it is slow, and the carbon carries the positive charge, so it is tertiary carbonium ion or carbocation, and so bromide ion is lost or halide is lost. In second step, the nucleophile attacks over this carbon having positive charge, and this second step is irreversible and is fast, and so there is summation of product. Now coming to last the comparison. So see, it is just opposite. It is just opposite with respect to this SN2 mechanism. Here it is SN1 mechanism. Why it is so? Because children, in case of tertiary carbonium ions, they are more stable because of presence of three alkyl groups. Three alkyl groups and alkyl groups, they provide stability. They provide stability because alkyl groups, they are electron releasing groups. So they push the electrons, and the magnitude of positive charge is decreased slightly. So as a result, when the positivity is more in the solution, so tertiary they react very fast, and so this is there. In case of secondary, there are two alkyl groups, and so in case of primary, so this is the change, and so it is just opposite that of SN2, and so this is all about the basic introduction about the chemical properties of the haloalkanes and haloarenes.